Let's look at a few examples of using the central limit theorem to find probabilities. We use the central limit theorem when we're being asked about the mean of a sample rather than about an individual value. And remember, in order to use the central limit theorem, one or the other of these things need to be true. Either the original population needs to be normally distributed or the sample size needs to be greater than 30. So let's look at the first problem. Cholesterol levels in men aged 18 to 24 are normally distributed with a mean of 178.1 milligrams per 100 milliliters and a standard deviation of 40.7 milligrams per 100 milliliters. What is the probability that the average cholesterol level of 25 randomly selected men aged 18 to 24 is higher than 190 milligrams per 100 milliliters? Well, first of all, we need the central limit theorem because we're being asked for the average of a sample of size 25. So the second question is, can we use the central limit theorem? Well, it is less than 30, but they told us that the original population was normally distributed, so we're good to go. So what we were told was that the mean was 178.1 milligrams per milliliter, and that the standard deviation was 40.7 milligrams per 100 milliliters. What we really need is the mean and the standard deviation of the sampling distribution. The mean of the sampling distribution, mu sub x bar, is just equal to the population mean, but the standard deviation of the sampling distribution is equal to the standard deviation of the original population divided by the square root of the sample size, in this case 25. And now let's go and look at some probabilities. So they asked us for the probability that x was greater than 190. So this is the case we have to say x is equal to 1 minus, and now we can go to our norm.dist function. 190 is the x they're asking us about. The mean is 178.1. The standard deviation is equal to 40.7 but divided by the square root of the sample size, which is 25. And cumulative is 1 because it always is in the normal distribution function. Okay, so our probability is 7.19%, and this is how we got that function. There we go. Okay, so that's problem 1. Problem number 2. Weights of newborn babies are normally distributed with a mean of 3,420 grams and a standard deviation of 495 grams. What is the probability that the mean weight of 100 randomly selected newborns is less than 3,375 grams? Well, do we need the central limit theorem? Yes, because we're not being asked about one baby. We're asking about the mean of 100 randomly selected babies. Can we use the central limit theorem? Oh, absolutely, because not only is our sample size greater than 30, we also have that the weights are normally distributed. So in this case, we have both conditions. We really only needed one. So let's remind ourselves that 3420 is the population mean, and 495 is the population standard deviation. The mean of the sampling distribution, still 3420, that doesn't change, but the standard deviation of the sampling distribution is our 495 divided by the square root of the sample size, in this case 100. Okay, well, guess what? They're asking us the easy one this time. So this time they're just asking us the probability that x is less than 3,375, and that's what norm.dist does all by itself. So we don't have to mess around with it at all. We just need to put in 3375, mean 3420, standard deviation 495 divided by the square root of 100. Cumulative is 1 because it always is on normal distribution, and there we have it. So we're talking about 18.17%. And here's how we got that function. All right, same question, same situation. Newborns, weight of newborns are normally distributed with a mean of 3,420 grams and a standard deviation of 495 grams. But in this case, we're asked about the average weight being between 3,375 grams and 3,505 grams. So yes, we need the central limit theorem because we're being asked about the average of a sample of 100 rather than about one newborn. And we can use it again because still the sample size is greater than 30, and we've also got a normally distributed population. So we've got 3420, we've got 495, we've got 3420 is the mean of the sampling distribution again, and once again to get the standard deviation of sampling distribution, we take the original 495 divided by the square root of 100, which is the sample size. Okay, now this time it's a little more complicated because we're talking about between. So we're going to start out with our norm.dist function, and we're going to do it for the higher figure, which is 3505. Our mean is 3420. Our standard deviation is 495 divided by the square root of 100. And our distribution is cumulative because it always is. But wait, 95.7 goes from 3505 grams all the way down to negative infinity, which is kind of silly because we can't have babies with negative weights, but nonetheless that's where it goes. But what we need to do is we need to come there and we need to subtract going from 3375 back down. So we have 3375 mean 3420, standard deviation 495 divided by the square root of 100. Cumulative is 1. And there is our probability that the average weight of those 100, what did I just do? There we go. Oh, I love the undo button, don't you? And there's our function. I hope that helped. Have a good one.